Sehr geehrte Frau Rektorin, liebe Kolleginnen und Kollegen, meine sehr verehrten Damen und Herren, es freut mich ganz außerordentlich, Sie zur Einführungsvorlesung meines Kollegen Dirk Helbing hier im Namen des Departements für Geistessozialen Staatswissenschaften begrüßen zu dürfen. Seit Juni letzten Jahres ist Herr Helbing Professor für Soziologie mit besonderer Berücksichtigung für Modellierung und Simulation. Er war vor seiner Berufung an die ETH Direktor des Instituts für Wirtschaft und Verkehr an der Technischen Universität in Dresden, wo er im Jahr 2000 zum ordentlichen Professor ernannt worden ist. Sein Studium der Physik und der Mathematik in Göttingen hat ihn nun aber etwa nicht, wie man vielleicht erwarten könnte, ans DESI oder ans CERN geführt, sondern hat ihn zur Beschäftigung mit nichtlinearer Modellierung und der Multiagentensimulation von empirisch beobachtbaren Selbstorganisationsphänomenen in Fußgängerströmen geführt. Er konvertierte also, wie er selber sagt, vom Physiker zum Soziologen. Ich finde diesen Ausdruck besonders schön. Es geht ja doch auch irgendwie um Glaubenssysteme. In seiner Dissertation an der Universität Stuttgart hatte er soziale Interaktionsprozesse mit spieltheoretischen Methoden, stochastischen Verfahren und der Theorie komplexer sozialer Systeme bearbeitet. Und diese Arbeit ist dann auch gleich doppelt ausgezeichnet worden. Nach seiner Habilitation über Verkehrsdynamik und Verkehrsoptimierung erhielt er 1996 ein Heisenberg-Stipendium. Helbing hat neben der Publikation selbstverständlich seiner Dissertation, seiner Habilitation auch zahlreiche Konferenzbände, zum Teil allein, zum Teil in Zusammenarbeit mit Kollegen veröffentlicht und die dafür notwendigen internationalen Tagungen und Konferenzen organisiert, die Themen wie Materialflüsse in Netzwerken und kooperative Dynamik in sozioökonomischen Systemen betrafen. Über 250 Referate und mehr als 200 Papers stammen aus seiner Feder. Sie sind unter anderem auch mehrmals in Nature and Science erschienen und haben wahrscheinlich auch deswegen für großes Aufsehen in Radio, Fernsehen und der Presse gesorgt. Seine Zusammenarbeit mit dem Weizmann-Institut in Israel, mit Xerox PARC in Palo Alto, mit INREDS in Paris und auch mit dem Collegium Budapest, diesem Center for Advanced Study, verweisen auf Helbings ausgedehntes internationales Netzwerk. Herr Helbing spricht heute über Physics, Sociology and the Clash of Cultures, from Crowd Intelligence to Social Inspired Technology. Als Historiker höre ich in diesem Titel natürlich auch eine Anspielung auf die Staatswissenschaften des 18. Jahrhunderts, die mit Justi, Süß, Milch, Getterle und wie sie alle hießen, davon geträumt haben, Massenphänomene so zu definieren, dass sie statistisch behandelbar werden oder gar so etwas wie eine Mechanik der Gesellschaft beschreibbar werden könnte. Nichtlineare Modellierung hat, soviel ist mir in früheren Vorträgen von Dirk Helbing klar geworden, die Materialien und die Dynamiken für diesen Traum stark verändert und möglicherweise auch die Grundlage zu neuen Sozialtechniken geschaffen. Aber vielleicht ist gerade dies auch Anlass für jenen Clash of Cultures, der im Titel Erwähnung findet. Ich bin sicher, Dirk Helbing wird uns darüber informieren. The floor is yours.
Thank you very much for the kind introduction. Welcome, ladies and gentlemen. Well, you may wonder why a physicist turns a sociologist, and it's not as strange as it may appear in the first moment. Actually, the father of sociology, Auguste Comte, he came up with the word of social physics. Later on, he used the term sociology, but he started up with a positivistic approach to the study of society based on observation and experiment, and he distinguished social statics, social dynamics, and as I said before, he already had this vision to approach social systems from a natural science point of view. he actually went one step further, stating that sociology would be the queen of sciences. That sounds quite daring, actually. But compared, for example, with biology and physics, the systems it deals with are the most complex ones. And that's actually also one of the reasons I decided to change to sociology, because there is so much interesting to discover. Unfortunately, until today, it still seems to be a dream, and the natural science approach seems to have failed to a large extent. So what is the reason for this? What makes quantitative theoretical progress so difficult? First of all, social systems involve a huge number of variables, and what makes it worse, they're often unknown, and empirical studies are limited for technical, financial, and ethical reasons. And moreover, there are all sorts of factors involved that we don't know so much from physics, such as memory, anticipation, decision-making, communication, and moreover, dimensions of interpretation of intentions and meanings. The nonlinear dependence of many variables, however, leads to complex dynamics and structures, which are difficult to describe, and often to paradoxical effects. That is another difficulty, of course. Furthermore, we face a problem of heterogeneity, so individuals are not identical. That's why they are actually individuals. There's social difference and specialization, and even the experimentalist, the observer, participates and modifies social reality even if he does not want to do this. So this really poses additional difficulties. So the conclusion is, if you want to understand this great complexity at the same time, we would be overwhelmed with details and facts. So my approach is to start with simple, well-measurable systems, such as crowds or traffic, and then eventually to proceed towards more complex phenomena. Now let's go back to some more prominent people in the social sciences. James Coleman, for example, said, social theory is a guide to social construction, no less than Newtonian mechanics is a guide to architecture and civil engineering. But he also points out that social theory has to face much more difficult tasks because of the complexity. Then there's Talcott Parsons. He advocated analytical realism, and he proposed that concepts in sociology should abstract from empirical reality with all its diversity and confusion in order to isolate phenomena from their embeddedness in the complex relations constituting social reality. And Herbert Spencer came up with analytical functionalism. He compared, for example, families, social classes, and cities with cells, tissues, and organs. And here we could make a link to physics because we find, in some sense, similar hierarchical structures. So elementary particles form atoms, these form molecules, and these form solid bodies, and so on. Such analogies have been further elaborated in systems theory, but the question is, what can we learn from such analogies? Is it just interesting to see them, or can we really progress scientific insight by this? So I would like to make some notes on general systems theory. Of course, there are considerable differences between physical, biological, and social systems, but there are analogies, and they suggest that there may be universalities and similar underlying mathematical laws. And for this reason, progress in the quantitative understanding of one system, for example, physical or biological systems, may be transferred, of course, with suitable adaptations to similarly behaving systems in sociology. For example, physics provides a quantitative theory of how hierarchical structures emerge, and with this a link between the microscopic and the macroscopic level of description. And this allows to draw some conclusions regarding interrelationships between things that seem to be different, such as structure, dynamics, and change. So there is a correlation between the hierarchical level, that means the social structure, its stability, the time scale on which changes take place, that means social dynamics, and the interaction strengths, that means social change. So in some sense, it draws together different dimensions of scientific research and of social and other systems, and that may provide, in fact, additional insights. There should also be, from my point of view, direct relationships between norms, deviance, and the speed of social change. Now, what can physics offer, maybe, to a better understanding of social systems? Now, physicists have learned how to describe complex systems. That means systems composed of many entities which are nonlinear interacting. And this description includes dynamics and timing, non-equilibrium and critical phenomena, instabilities, phase transitions, that means changes in the qualitative behavior of systems, and extreme events. Furthermore, interaction effects in space and in networks. Furthermore, collective behavior of many interacting entities, effects of history dependence, and the influence of heterogeneity, that means individual differences or social inequality, and implications of stochasticities, which is a description of uncertainty and risk, and the emergence of new system properties through self-organization based on nonlinear interactions. So let's try to make it a bit more concrete by a few examples, and so I would like to enter the chapter of evidence-driven modeling, starting with pedestrian dynamics, and would like to put my focus on self-organization and crowd intelligence. So, if you would observe pedestrian crowds, in the beginning probably would just look quite confusing, but recording it and accelerating the recordings will reveal unexpected behaviors, such as the formation of lanes of uniform walking direction. It means people are just not just walking in a mixed, chaotic way. Here we have predominantly people walking on the right-hand side, and people from the opposite direction are walking in different lanes. So there is a separation between the different directions of motion. And the question is, why does it happen? Most people are not even aware of this. It's obviously something like macroscopic social structure that is based on individual interactions on the so-called microscopic level. Now, we have come up with a model which is very simple, actually physics inspired. I will show it later on to you. And here is a simulation of this model. You see, we represent people in a particle-like way. So they're entering this corridor from the right and the left at random positions, and then after a short distance they're walking behind other pedestrians. And this is not because we have implemented a model that assumes people would follow other people. In fact, what we have assumed is that everybody wants to walk into this or the opposite direction, and there are repulsive effects between the different people, making them to keep distance between each other. And based on these very simple rules, it turns out that after a short time, people are self-organizing into lanes. Now, this is because whenever two people meet, they have to step aside a little bit so that it constitutes a separation tendency, and once they're walking behind each other, it's much more efficient. There are less interactions with the opposite direction of motion, so for this reason, this pattern is stable, and this is why we actually see it. In fact, what is important is that people walking into opposite directions have a higher interaction frequency than people walking into the same direction with a similar speed. Now, this pattern of motion reduces obstructions in the flow, and it increases the average speed. So the efficiency somehow, and one could say, okay, that's an intelligent behavior, although we don't tell the people, okay, now organize yourself in a way that is lane-like and which is intelligent. It just happens by very simple local interactions. And there are many other examples, of course, in crowds where we find that based on simple interactions, intelligent structures and dynamics comes about. So how do we describe this behavior? We have developed the social force model, which assumes individual goals, it means to reach a certain destination efficiently, social interactions, for example, avoidance of collisions, and institutional settings, for example, walls. And it is composed of several forces. They're written down here, by the way, so they're driving forces, which describe the adaptation of the actual velocity towards a desired velocity in a desired direction of motion that takes a certain time. And there are repulsive forces, which reflect that people try to avoid collisions. And there's a territorial effect in some sense. And there could also be social attractive forces among group members, of course. And furthermore, we have repulsive interactions with walls, and there are additional fluctuation terms which are not written over here, which may take into account the individual variability of behavior. Now, as you can see here, we have just added up those different forces representing different intentions of individuals to determine the acceleration of individuals. And then in addition, we have this equation of motion, which just states the trivial point that the change in space is given by the speed of pedestrians. So it's a quite simple model. It's similar to models from physics, in particular from mechanics, but we have additional points which reflect differences between physical particles and individuals. For example, this driving force and these intended directions of motions and other things that distinguish those forces from physical forces. Now, why does this model work so well in practice? Now, it's because pedestrian behavior is simple, it's a standard behavior, and also it's constrained by other people's motion. So there are not so many degrees of freedom. There are other interesting phenomena, such as oscillations at bottlenecks, as you can see over here. So again, people are walking to opposite directions, and there's a conflict of spatial usage over here. You can see it's resolved by an oscillatory organization. So for some time, people from one side are passing the bottleneck, and then for some time from the other side. In some sense, one could say, okay, those people who have to wait are increasing in number because more and more people are arriving. So in some sense, a kind of pressure builds up, and when this pressure is large enough, it stops the opposite stream and people will pass from the other side. And this works quite well. It's another example of macroscopic organization based on individual local interactions, which appears to be quite intelligent. Now, this also has practical implications. Knowing about the self-organization of people, it turns out that standard elements of pedestrian facilities, such as corridors, bottlenecks, and intersections, could be designed in a better way, using the self-organization of people. And so here is an example which shows that those series of columns actually helps to separate opposite directions of motion, this way avoiding kind of friction between opposite directions of motion. In the meantime, also, this has entered a software which is now commercially available through our partner PTV, so it's now used for planning of pedestrian facilities and traffic systems and mass events. I want to enter now another subject where humans are involved, which is traffic dynamics. Now, also here one could say individuals have a freedom of will, so how should it be possible to describe their behavior in a mathematical way? But there are some stylized facts, and these can be mathematically represented quite well. And again, we have the situation that cars constrain each other's motion, and also, of course, people usually want to stay on the road. Now, actually, one could say thinking in stylized facts, which is a modern approach to complex systems, has its root much earlier. So, for example, Max Weber proposed to elaborate ideal types as abstract statements of the essential, though often exaggerated characteristics of social phenomena in order to sharpen comparisons. The ideal types serve to be contrasted with the actual empirical reality, so in some sense they're even wrong by kind of oversimplifying, but still one can learn from this. Today, we would maybe call this stylized facts. And here I want to present a few of them regarding the situation in traffic flows. This is a recording I did in Cairo, and it's a big road within the city. There are no traffic lights down here, but we will be the witness now of the emergence of a traffic jam. So you can see it just happened over here. The question, what is the reason? You can also see the traffic jam moves backwards. That's one of the stylized facts we want to understand later on. Actually, that is described quite well. And you can see here is an entering road, an on-ramp, which produces perturbations in the flow, and it has actually triggered the breakdown of traffic flow. Now, here are some empirical examples of congested traffic states. It's quite surprising that we have such a large variety of congestion patterns, and obviously that have to be reproduced by mathematical models. Now, it turns out that most traffic jams are generated by a combination of three facts. Again, stylized facts in some sense. So a high traffic volume on the one hand, an inhomogeneity along the road that could be an on-ramp, or it could be the reduction of the number of lanes, or it could be a slope. And finally, a perturbation in the flow. So here you can see it started as a very small perturbation in the flow, and then finally it caused the breakdown of the traffic flow. So the higher those structures are, the slower is the velocity and the higher is the density. Now, how can you make sense of this complexity? Can we just give up facing this large number of different traffic states? The answer is no. Actually, traffic models have been quite successful in reproducing these patterns, and here you see simulation results for one macroscopic kind of fluid dynamic traffic model. And in these models one can study in simulation experiments certain behaviors which are hard to observe. So for example, perturbations in traffic flow reduce the capacity, or can reduce the capacity, and even a reduction of the traffic flow could, under certain circumstances, cause congestion. So that is quite surprising, I would say. Now, I should also state that there is not only one traffic model which can produce such kind of patterns. Maybe unfortunately, because coming from physics reviews, there is one Schrödinger equation or Newton's equations of motion, and if you look into the recent literature of traffic modeling, there are probably more than 100 different models. So in some sense, every author has his or her favorite model, and that's not a very good situation in some sense if you are hoping for convergence. However, it turns out that one can classify these 100 and more models, and this can be done in terms of phase diagrams. So these phase diagrams can be used for different things. First of all, they predict under which kind of circumstances, in terms of the on-ramp flow, for example, and the flow on the freeway, there's free traffic or different kinds of congested traffic. And those separating lines for which we expect a transition from one kind of traffic to another kind of traffic can be mathematically calculated. That's a nice thing. On the other hand, one can compare phase diagrams of different models, and one could say those models that produce the same kind of phase diagrams that are mathematically equivalent. So they fall into the same universality class. And we could pick any of those models from the same universality class because they're behaving more or less the same, qualitatively the same. So that is very useful, and one could even say, okay, then we just take the simplest or the most accurate. However, as in these kinds of systems involving humans, there's usually a relatively high degree of variability. The different models don't distinguish themselves so well in terms of the quality of reproduction of empirical data. So one could really say, let's just go for the simplest model that can produce the stylized facts. And of course, some of the models don't reproduce all the stylized facts and all the empirical traffic jams we have observed, so that would fall in a different universality class, and that would not describe real traffic flow. They would describe something else. So this helps to make sense of the huge number of models and huge number of phenomena, and one can here learn a lot from the notion of universality. Now, can engineers learn from social scientists? I would say yes, because technological systems are becoming more and more complex. Today's systems are multi-component systems in many cases. We're talking about ubiquitous computing involving millions of chips and these kinds of things, and it's not possible to control these systems centrally anymore. And due to this complexity, engineers are reaching out for decentralized control algorithms that would, by self-organization, lead to a high degree of order and favorable organization in the system by itself. And in fact, social systems are such kind of complex systems that do self-organize. So learning how this happens in social systems allows engineers to learn how to optimize technological systems. And I want to give you 2 examples related to traffic. So you remember we had this observation of oscillatory flows at bottlenecks. And in some sense, intersections in urban networks are also bottlenecks. And when we have traffic light controls, we implement by force, in some sense, oscillations in those traffic flows. The question is, couldn't we implement a mechanism that would lead to self-organized oscillations, and in this way establish a self-organized traffic light control? And in fact, it's possible, and I want to demonstrate this in this simulation over here. You can see that there is a tendency of green waves, so many of those platoons are passing several intersections after each other. Now, let us try to figure out why this works so well. Now here I show in green traffic lights that are green for north-south or south-north direction. Red corresponds to traffic lights that show green for east-west or west-east direction. Now what we can see over here is that neighboring intersections tend to be synchronized. That means show the same kind of traffic light. And there are islands of these synchronization patterns that are, however, changing all the time. It doesn't repeat this pattern, and somehow this ever-changing structure shows the flexibility that this self-organized traffic control has with respect to the local traffic situation. Now the problem is actually that we have to solve. The problem is to find the optimal compromise between coordination and local flexibility. If we had the maximum degree of coordination, then all the traffic lights would be switched in the same way everywhere in the network. But then we would not have any flexibility with respect to the local traffic situation anymore. So we need to have more flexibility. And on the other hand, if all the traffic lights would just look at the local situation, the traffic jam that has formed just at this traffic light, then there would probably be a low degree of coordination between the different traffic lights. And then something is established which we call a social dilemma. Everybody is behaving in a selfish way, although the different traffic lights are doing their best locally. The overall performance is not good. Now, this has actually been also applied to more complicated traffic networks, such as the city of Dresden, and there's now even a practical pilot study going on. Why is this self-organized traffic light control so interesting? Because it can reduce delayed vehicles a lot. So today's cycle-based controls are represented by this line over here. And you can see that the result that we can reach by self-organization is much below this, meaning a much higher performance. And the difference between today's traffic light control and that the one we are proposing is even more increased when the variability in the inflows is large. Now, why is the self-organized traffic light control so successful? Because it's flexible. It does not just repeat one cycle again and again and again. It allows for varying patterns, and could even happen that one street is served twice, while another street where only a few vehicles are arriving is served only one time. Moreover, you can see if you look at the frequency distribution of the service intervals, then we don't have periodic behavior, otherwise we would have just lines over here. But you can see we have a distribution, and that shows two things. So it's an almost periodic control, but these small deviations from periodic control can reach a much higher efficiency. So I think that's quite interesting, and that's why we also patented this. There is another system we have been looking at, which is freeway traffic. And as I told you before, it can happen that small variations in the flow can trigger a breakdown of traffic flow and even reduce capacity. And this happens during rush hours. That means during times when we need more capacity rather than less capacity. So that shows that self-organization not always produces good results. The question now is, can we change the interactions between the vehicles in a favorable way, in a way that supports cooperation among the vehicles, which makes traffic flows more stable and also increases the capacity of traffic flows. And in fact, this can be done. And the concept involves different elements which kind of share features that we know from humans. So there's, on the one hand, something like a very simple perception. I mean, onboard data acquisition by means of radar sensors and speed measurements and these kinds of things. Then we have something like a primitive cognition. So the cars are trying to make sense of the measurements in terms of trying to determine the traffic states they're in. Then there could be inter-vehicle communication, which allows to find a collective agreement on the individual assessment of the traffic situation. And this information about the traffic situation is then used in terms of decision making to adapt the driving strategy to the particular traffic situation. One could then inform the driver, or one could have the car automatically take control and do what would be a good driving behavior. And this is what we call traffic assistance. There are experiments already going on with cars that are equipped with this kind of traffic assistance systems. That is a collaboration that is going on with Volkswagen. And here is an evaluation looking at what would change if we would have 10% equipped vehicles or 20% equipped vehicles with respect to today's traffic situation. So here's an example of the breakdown of a traffic and we have congestion forming quite pronounced, and you can see 10% equipped vehicles would reduce the extension of congestion a lot, and 20% equipped vehicles in this scenario would almost avoid traffic congestion to occur at all. And the good thing is that we don't need to equip 100% of vehicles in order to reach positive effects. In fact, already between 20 and 40% we have very large effects, so that's very important for a successful market introduction strategy, because you can never equip all the vehicles at a time. If you want to reach an effect, nobody would buy the system if it wouldn't have an immediate positive effect, such as higher driving comfort or personal gains in terms of reduced travel times. So the system has different advantages. So traffic breakdowns are delayed. There's faster recovery to free traffic. The travel times are reduced considerably. You can see it during congestion times. We have an increase by a factor of, for example, 3 to 4 in travel times. And with the new system, if only 20% of vehicles were equipped, the travel times would almost stay the same. And there are also very positive effects on fuel consumption and emissions. So one could call this mechanism design, as we're changing the interactions of the vehicles. And here is a simulation that first of all illustrates the emergence of a stop-and-go traffic jam in a computer simulation, and we do something that usual drivers can't do. We sit into a helicopter. That's, by the way, our coffee meter, and it measures changes in acceleration which people may find uncomfortable. Now we use the trick, and what we can see now is that this on-ramp is the reason for the forming traffic jam. We're now accelerating the simulation a bit to save your time, and then we're turning on this new traffic assistance system without reducing the inflow. So we have still the same heavy load, but what you can see is that after a short time, even this traffic jam is resolved. So that's something we're hoping for in the future. May still take a few years until it's finally practically applied, but as I told you, companies are already working on it and testing it. Now I like to switch to another approach to describe social systems, which has been very successful in terms of mathematical description. The game theory, that doesn't sound like a serious scientific approach, but it's actually a very powerful mathematical discipline to provide tools for the explanation and prediction of interactive decision situations when goals and preferences of the participating players are potentially in conflict. And the milestone book was published by von Neumann and Morgenstern in 1944, Theory of Games and Economic Behavior. It's still a very, very active field, and I want to show you how it can be used, for example, to understand this preference of the right-hand side that we find in pedestrian crowds in many Western European countries, or of the left-hand side, which is found, for example, in Japan. Now, one important point is that social interactions between two individuals are characterized by a mathematical quantity which is called the payoff. And here you can see, okay, we have the two pedestrians. Each of them has two different strategies, either avoiding someone else on the left or avoiding someone on the right. So when two people interact with each other, then they would get a certain payoff. So, for example, if both avoid each other to the right, then that was a successful attempt to avoid each other, and we would quantify it by a benefit, because it saves time compared to a situation where one person is avoiding the other to the right and the other to the left, and then again they're standing in front of each other and haven't succeeded in avoiding each other. So we give a payoff of 0. So using the same avoidance strategy is beneficial. And now one can assume that people would profit from following the trend in a population. And if we assume that people would imitate the more frequent behavior because it's successful more often, then we would end up with a differential equation which describes the change in the proportion of people using strategy I, which means, for example, to avoid people on the right-hand side. And setting this to 0, we determine 3 stationary solutions. So one of them is half of the people are avoiding the other on the left-hand side, and half of them on the right-hand side. And there are two other solutions corresponding to 100% of people avoiding on the right-hand side and 100% of people avoiding on the left-hand side. Now it turns out that this solution is unstable, so what happens is that even if in the beginning 50% are using left-hand side and 50% are using the right-hand side, just by small fluctuations in the number of people applying one strategy, eventually we would end up with the majority using one side. So by this approach, we can understand the self-organization of a behavioral convention, and also why in some countries people prefer the right-hand side and in others they prefer the left-hand side. But the most famous game in game theory is the prisoner's dilemma. And this is reflected over here. So we have two different strategies, cooperate or defect, which is not cooperate in normal language. And so if people cooperate, they get a certain relatively high reward, and if they defect, they would be punished by a lower payoff. However, what makes this thing exciting is that if one person defects and the other cooperates, then the defector gets an even higher payoff than this reward. It's called the temptation to defect, and this is called the sucker's payoff, which is assumed to be smaller than the punishment over here. So the cooperator would be worse off than if both would defect. And why is it called the prisoner's dilemma? Because it reminds of situations which are actually applied in practical situations. So just assume two criminals have been caught by the police, but the problem is to materialize the evidence against them. So what they promise them is, okay, if you tell us what you have done, and in particular what the companion has done, that means the other person has done, then you go free, and the other one goes into jail for 5 years. If you don't tell anything, then we will charge you for tax fraud or something like that. We will find something, or traffic violation or whatever. And if both now are tempted to defect, and both are telling the facts to the police, then they're both put to prison for 2 years. And in many situations we are facing, even if we are kind people and not criminals at all, are reminding this kind of prisoner's dilemma. Actually, social dilemmas have a very similar structure, and they're, for example, describing the tragedy of the commons, that people have to contribute to a public good, but there's a temptation to free ride, and if everybody does it, then the result will be very bad. Now, it is known that in these kinds of situations, the most likely result if people interact 1 time would be defection of both individuals. And the question is, how can we increase the level of cooperation in these kind of dilemma situations? And 5 mechanisms are well known, as pointed out by Novak, and these are genetic relatedness, also called kin selection, repeated interaction, sometimes related to the term shadow of the future. This is also called direct reciprocity. Then reputation, which is called indirect reciprocity. And clustering, which is also called network reciprocity. And finally, competition, also between groups, that means group selection. Now, the clustering of cooperators is, for example, observed in the spatial prisoner's dilemma. And here we assume that people are distributed in space. We have kind of a chessboard. Each field of the chessboard is occupied by an individual. And then everybody is playing the prisoner's dilemma with the 8 neighbors of the chessboard. And then gets a payoff with each of these 8 neighbors. This is summed up, and then what happens is everybody looks how big was the payoff of the neighbors, and someone was better off, then the strategy of this neighbor is copied. So people imitate successful behaviors, and under certain conditions, what one can find is a kind of chaotic pattern formation as indicated over here. Now, these patterns don't look so realistic from the point of view of social systems. I don't believe you have ever seen these kind of chaotic patterns happening. And so the question is, can we come up with a model which describes social interactions in space more realistically? And moreover, can we combine those 2 successful approaches of interactions in space of time, as we have looked at for pedestrians, with a game theoretical approach? And in fact, what we have done is we have introduced success-driven motion. So individuals are assumed to have a preference for a favorable neighborhood, and they would tend to move into this neighborhood in order to increase the payoff. In fact, the phenomenon of directed migration is very widespread, so we observe it for humans, for animals, even biological cells. And so assuming diffusive motion would certainly not be realistic. And sociology and biology are full of examples of niche and class formation, of agglomeration, and so on, also segregation. So these are phenomena we would like to be able to interpret in a generalized game theoretical context. And so what we have done is we have generalized the spatial prisoner's dilemma by May and Novak by adding a success-driven motion step before the interaction and imitation steps. And how does it happen? First of all, we assume that not all the spaces on the chessboard are occupied. There are free spaces where you can move to. And people would look into a certain neighborhood. It means, for example, 2 fields away. They would check out every free space in a test interaction, and if they find it would be a more favorable environment, then they move over there. So this resembles relocations, for example, between apartments, and also it reflects that people occupy a certain territory. There are different mechanisms that we can think of, for example, wealth-related tagging. So usually you see how wealthy a neighborhood is. So in some areas there are big villas, in other areas they're not. So you may draw a conclusion regarding the degree of cooperation or the level of payoff in this area. Okay, and if we do these kinds of simulations, then we find that compared to the imitation-only case of May and Novak, we find a different dynamics in space and time. So let's look at the migration-only case. Here you can see that neighborhoods are a bit more pronounced than in the imitation-only case. And what is really interesting to see is when we have imitation and migration together, then there is a clear formation of structures, so kind of urban agglomeration, one could hypothesize. And moreover, the larger level of blue over here indicates that there's a much higher level of cooperation. So migration is a way of increasing cooperation a lot. Now, can we use these kinds of insights in order to improve society, as Auguste Comte has actually proposed it. And Max Weber also indicated that sociologists should be involved in politics, however, outside of the classroom. And I want to give some modest examples where actually scientific insights can make improvements. Here's a list of problems that can be addressed and that will be addressed actually by the currently established Competence Center on Coping with Crisis in Complex Socio-Economic Systems, in which various colleagues of ETH are involved. So, for example, what is the impact of scarce resources on socio-economic systems, for example, conflicts, and how to distribute them optimally and fair? What factors and conditions destabilize socio-economic systems? We have seen the breakdown of traffic flows. What are network effects in this relationship? What about the scalability of institutions? Potentials, design, and limitations of decentralized control? And how to reach robust organizations and optimal crisis management? Yes, and some examples are stock market crashes, cascading failures related with disasters, wars and conflicts, and crowd disasters. And I want to address 2 points over here, which is conflicts. So we have started now to simulate something one could call a clash of cultures. So what are cultures? Cultures refer to a set of symbols and meanings, including values and norms, and these are regionally different. So if people from different regions come together, then it could happen that partially incompatible cultures start to mix. And the question is, would there be unilateral adaptation? Would there be mutual adaptation? Would there be conflicts or segregation or a combination of this? And well, we have some first results over here, but this is work in progress, and you can see very interesting dynamics going on. And we hope to learn from this in order to see what could happen in certain scenarios. For example, if you have two neighboring countries and then you lift the border, people can move across the border. And here are two simulations, one assuming a gap in the wealth of the populations, another assuming an education gap. And as you can see, both will not cause the vanishing of civilization. So cooperation is likely to survive, and actually it may even spread into the other population, even if the level of population was small, but it depends on the situation. Now, one very difficult problem to solve are crowd disasters. Now, people are certainly interested in this because we have now the Euro Cup in Switzerland in a few weeks. And I'm sure the preparations have done well, so these kind of scenarios would not happen. But as you can see, in the past it happened quite often, and many people have died. And there are surprising effects, like people could not even leave emergency exits because somehow they block each other. And one study we have performed was for the annual pilgrimage in Mecca and surrounding. And the problem that people faced was that within some decades, the number of pilgrims has increased from a few 100,000 to 3 million, and is expected to grow even further. So it was more and more difficult to perform the religious duties, and the religious sites did not provide enough capacity anymore, and it caused crowd disasters. Many people died. And this was the situation at the Jamarat Bridge that has now been torn down and replaced by a new, bigger structure to allow for more pilgrims. Well, what happened in 1996 was that there was a big crowd disaster on this plaza, that means in open space, and the question is, how could this happen? And as for some reason, video recordings have been done. In this case, there was video material that could be evaluated, and you can see is that somehow there was a merging of different directions of flows, and that caused a bottleneck in some sense. What was surprising is that there was a transition from smooth to stop-and-go flow, as you can see over here. And it turned out that it is not primarily the density that explains these transitions, but it is, in this case, a change in the flow. Yes, in fact, well, if the density exceeds this level, then the flow breaks down, the capacity goes down, and then we observe these stop-and-go patterns. And our explanation is that people are competing for scarce space, and as a result, we find intermittent outflows, so an alternation between downward pedestrian flows and upward gap propagation. Here's an example showing that if people are in a rush and pushing too much, then the outflow is temporarily interrupted, and this is something that one would like to avoid because it reduces the capacity, as I have indicated. But the situation becomes even worse when stop-and-go flow turns into a state that we call crowd turbulence. So this is a normal motion of a pedestrian, and these are stop-and-go waves. Now we can see in a turbulent situation, people would even temporarily move backwards. In fact, they would be moved into all sorts of direction. And so it's difficult to control the own motion and keep yourself on the feet. And that's a situation where crowd disasters are likely to happen. Now you can see over here a video that shows that people are shaken around in this crowd, and this is a very difficult situation. You've also seen we have highlighted the pressure in the crowd, because it turned out there is a way to quantify the hazard, and this is done by the pressure, which is the density times the variation in speed. And so after having learned about the reasons for this crowd disaster, of course, measures had to be taken to improve the situation. In fact, several measures had to be combined. So this included, for example, scheduling, means timing when people are leaving the tents for performing the religious duties, flow monitoring, and adaptive rerouting. And also, the flow has been organized in a different way. So while that was the situation in 2006, characterized by large accumulations, dense crowds, and long exposure times to intensive sun, in 2007, we had unidirectional smooth flows, and Pilgrim liked and supported the new organization a lot. So with this, I would like to conclude and state that starting simple allows making progress in terms of mathematical modeling. So in some sense, less is more. And it is possible to understand the self-organization of macroscopic structure and dynamics from microscopic individual interactions. One example I showed you is the emergence and breakdown of coordination or cooperation, and models of instabilities and transitions between different system states are getting practically relevant. So there are interesting developments concerning engineering applications and how to cope with crises in socioeconomic systems. And further progress is expected from the exploration of new kinds of data that are currently becoming available on social behavior, such as experimental games, data from the Web 2.0, interactive games like Second Life, neural imaging, consumer behavior data, communication statistics, sensor technology, video tracking, and so on. But this requires funding, as in the natural and engineering sciences. So, given a joint international interdisciplinary effort, will Auguste Comte's dream eventually come true? We will see. Thank you for your interest. I would like to invite you now to participate in the reception outside, where you can also ask questions.